In this video, we're going to discuss about the RMS voltage, which stands for root mean square voltages. We're going to discuss this concept a little bit, right? So the first thing to keep in mind that we're still discussing about a voltage measurement. So the unit of RMS voltage should always be in volts. This will be really important when along our discussion on the exact mathematical operations required for computing RMS voltages, right? The main reason why we introduce this concept of RMS voltage is we want to compare the performance of different waveforms. So be it a sine wave, triangle wave, or square wave, especially when they share the same magnitude, frequency, and phase. How do we tell them apart? Right? So right now you might have an idea that okay, since I have the same magnitude, we really can't just compare the magnitude or the frequencies or the phase, right? Something might worth doing is maybe summing or doing an integral over a period for these signals and see what are the values, right? So this is exactly the backbone of RMS voltage calculation, right? So let's take a deeper look into this. The first thing you do in calculation of RMS voltages is that you square your signal, which is typically a voltage signal, right? Why do you do that though? First thing you might be thinking, okay, if I do an integral over a period, you still have a negative portion of these AC signals, right? You want to bring that negative portion to a positive one. So one of the most natural way to do this is just square the signal. And this is exactly half of the answer. And the other half of the answer is that operation of doing the square actually have a physical meaning, because your input signal is a voltage, and if you square a voltage, voltage square goes with power. Voltage square is proportional to power because of Ohm's law, basically. So the first thing you do is square your voltage. You get a sense of the signal's instantaneous power. The second thing you do the integral. You sum all the power over one period. So at this stage, what you have is the total transmitted power over a period. Then you do the time average power, right? At this point you have. And the fourth thing you do is you do a square root. Why do we do that? Because remember, the first thing we do is we square a voltage, right? But remember, at the end, we want the unit to be still in volts, because we're talking about the voltage reading, right? So we want to bring that unit from power back to volts. So that's why we're doing a square root in the end. So after this discussion, you kind of have an impression that the RMS voltage is really evaluating a waveform's time average power, but the unit is still in voltage. So what it exactly means is that, let me take an example, right? So if you have a sinusoidal wave of peak-to-peak value of 5 volts, let's say this is in your pre-lab, right? So VRMS of that signal is around 1.77 volts. You did the calculation already. So what that means is a sinusoid of a magnitude of VPP equals 5 volt carries the same time average power as compared to a constant DC voltage at the voltage value of that VRMS equals to 1.77 volts. That's exactly the story about VRMS and the meaning of VRMS. So a question for you right now. Are you able to tell me between square waves, triangular waves, and sine waves, don't do any calculation yet, which one has the largest VRMS value?